speaking about Kafka and the future of real-time event streaming. So I am very excited to introduce the speaker of the evening. She is Satabdi Mishra, working as a data scientist intern at MOHS10, huge ML enthusiast, and today she will be speaking about the Kafka and the future of real-time event streaming. So now I would like to invite Shatabdi to throw more light on this topic. So welcome, Shatabdi.
Thank you, Glorina, for the wonderful introduction. And thank you, MOHS10, for providing me with this wonderful opportunity. So I guess we are good to start. Let me present my screen. So is my screen visible, guys?
Yes. Shatabdi.
Okay, so the topic upon the table today is Kafka and the future of real-time event streaming. And let me walk you through today's agenda without further ado. So today we'll be covering a brief overview about event streaming and Kafka as an event streaming platform. Then we'll be addressing certain pivotal questions like why Kafka and what can Kafka do. Later, I'll be walking you through the Kafka architecture, use cases, applications in the industries, capabilities, major challenges, and future scope, in which I'll be comparing another product of Apache, that is Pulsar versus Kafka, and then going to the conclusion. So, in the current present scenario of the industry, we have seen a paradigm shift from a static snapshot to a continuous stream of events in the consumption of our users. There has been a shift in the favor of event-driven frameworks and architecture. So we are now getting used to consume a constant feed about the activities of all our friends in the form of Facebook and Instagram feeds or Instagram and Facebook lives. We are also acquainted with real-time news feeds accessible online anytime, anywhere in the form of Google News or Twitter feeds. This has led us to create a platform which can be a single integrated platform to connect everyone to every event and stream events in real time. We also want to store these events for historical view or retrospectively for later retrieval. Now let's discuss the two kinds of firms that are born out of the need in the current crisis. Some of these initiatives or firms are born cloud native, like social networks, which enable event sharing, streaming providers that provide on-demand digital content, and ride-hailing providers that connect providers with consumers in real time. And also there are traditional ones that are trying to adapt, like newspapers, credit card payments, finance, like always had protocols and legacy systems since ages, and of course the cars, which are trying to get automated using IoT devices and use real-time traffic routing. Now let me review a brief overview of what streaming actually is in a sense. So event streaming is the practice of capturing data in real time from event sources like databases, sensors, mobile devices in the form of stream of events, storing these events directly for later retrieval, manipulating, processing, and reacting to the event streams in real time as well as retrospectively, and routing the event streams to different destination technologies as needed. So as you can see on my screen, there is a single event source, and then you can see different events being processed under an event stream. This is basically our topic. It is a basically queue with the functionality of first in, first out, with some added processing event streams. The event 4, E4, is referring to the newer events, and the event E0 is referring to the older events. And all these events are being streamed and processed in this topic. And later, they are deployed to various event sinks and applications as per their requirements. Now going to go Apache Kafka and its role as an event streaming platform. So Apache Kafka is a high throughput distributed streaming system used for stream processing, real-time data pipelines, and data integration at scale. So in the previous slide, we already discussed about streaming systems. Now let me walk you through the different kind of systems we have in general. So one is centralized system and the other is distributed system. The centralized systems generally run under a risk of data loss because the data is actually stored at a single point. But in the case of distributed systems, we can have two scenarios. Either we can split the data into parts and replicate them to destination systems, else we can make replicas of the data and replicate them into the destination systems. So Kafka is configurable to both this kind of scenarios as per the user requirements. Also, Kafka is high throughput, which means it acts in real time with latency that goes to as low as 2 microseconds, which is huge. Originally, Kafka was created to handle real-time data feeds at LinkedIn in 2011, but it quickly evolved from a messaging queue to a full-fledged event streaming platform capable of handling over 1 million messages per second. Today, as I'm speaking, it is being used by 70% of the Fortune 500 for high-performance data pipelines, streaming analytics, data integration, and mission-critical applications. On my right-hand side, you can find a picture where you can see how Kafka can be coherently integrated with many platforms and tools like Salesforce, SAP, Workday, Oracle, and several others. Now going to the most trivial question that I would like to pose to all of you. Why Kafka? Why is decoupling data streams and systems necessary? So on my screen, you can have a look at three systems, System A, System C, and System E. These are basically the source systems, and the systems below, System B, System D, and System F, are the target systems. So the total number of integrations possible between these systems is 3 into 3 equals to 9. But let's suppose I try to add 2 more systems in the source, and let me make the number of target systems 10. So the total number of integrations now possible is 10 into 5 equals to 50, which is huge. Can you understand how complicated and messy the architecture will become? And it will also become highly unmanageable. Also, there may be issues related to data formats, data protocols, and data schemas and the revolution. Also, connecting all of this through real-time data pipelines and batch pipelines to a data lake will make it highly messy and complex. So let's see how Kafka helps us to reduce this kind of problem and mitigate this risk. So as you can see, Apache Kafka as a distributed streaming platform is acting as a middleman here. System A, System C, and System E are still the source systems, but they are directly feeding in their data to Kafka. And System B, D, and F are directly retrieving the type of data they require from Kafka directly without getting connected directly to System A, C, and E. Kafka can also be linked with the data lake for further connections of real-time and batch processing. And this all can be done because Kafka enables loose coupling between the systems. So we can add as many number of systems as we want without increasing the complexity of integrations. And this architecture is highly scalable and manageable. And instead of multiple integration protocols and data format types, we just have to manage the few protocols and data Kafka supports. Also, Kafka is highly performant and supports both real-time and batch use cases. Having said this, let me walk you through a flow in the real-time enterprises and how it is Kafka is getting used by the industries right now. So as you can see in this flow, we have our data producers like apps, websites, financial systems, email, customer data, and databases. And these data is basically getting fed into Kafka. And Kafka is feeding it further into its components like Spark, Storm, Flink, etc. And then this is going through real-time data pipelines for analytics, dashboarding, and for alerting customers in real time. Can you imagine how impactful this is? Next, Kafka can also be integrated with many big data tools like Hadoop, Amazon S3, and relational database management systems for data science analytics, reporting, audit, backup, and long-term storage. And this all goes under batch pipelining. So this is how the flow created says why Kafka is trendy currently in the market for various data-driven firms. Next, exploring what are the core functionalities of Kafka and what can you really do with it. The first thing is, of course, you can create your own events with your favorite programming languages like say Java, Python, Go, and then push this as producers to Kafka streams via APIs. So in Kafka, you have 4 types of APIs: the producer APIs, the consumer APIs, the stream APIs, and the connector APIs. You can also use the 𝐀𝐩𝐚𝐜 database, which is a streaming database tightly integrated with Kafka streams to create, process, and query event streams and tables. Along with that, you can also build your applications and read and process event streams in Kafka. You can also import data as event from the cloud and export data as event from the cloud using the Kafka cluster. Last but not the least, you can build a highly elastic and scalable streaming storage using the Kafka cluster. So this was a brief overview about the functionalities in the core for Kafka systems. Now let's have a sneak peek at the Kafka architecture. So as you can see on my screen, there are 4 major components of the Kafka architecture. First is the producer, which is responsible for pushing, publishing, or writing messages into the Kafka cluster. Second is the consumer, which is also known as the consumer group. I'll say about it later in the slides. So basically, these consumers are responsible for pulling messages or consuming messages. They are the end users. And there are, of course, the brokers. Brokers are basically servers, and they are used for load balancing in Kafka clusters, since Kafka clusters deal with humongous amounts of data sets. And these brokers are basically responsible for serving and receiving data. One important thing to note about these brokers is each broker is uniquely identified with an ID, which is basically an integer. So broker 1, here 1 is the ID, broker 2, 2 is the ID, and so on. And also numerous brokers compose the Kafka cluster. The Kafka cluster and the zookeeper are collectively known as the Kafka ecosystem. Now, what is the function of the zookeeper? So the zookeeper basically coordinates and monitors the Kafka brokers, and it also notifies the producers and consumers about addition of any new broker or deletion of any broker in the Kafka cluster. The producers and consumers also update the zookeeper about the Kafka broker ID and offsets. And this is how the entire architecture of Kafka looks like. Going to the next slide, we are going to discuss about another yet important topic of Kafka cluster, that is topics, partitions, and offsets. Topic is nothing but a particular data stream in Kafka. It is analogous to tables in databases. We can create as many number of topics we want in Kafka, but there is a limitation here. Each topic is uniquely identified with its name. So we cannot have 2 different topics with the same name. So suppose we, for an e-commerce company, we create a topic which is order, and we create another topic which is budget. So in the order topic, we have to process all the data related to the orders. And in the budget, we have to process all data related to the budget of the company. So this is how topic works. Now let's see what are partitions. So these topics, for becoming a distributed system, are split into several partitions. So as you can see on my screen here, a topic is divided into n different partitions. And also these partitions store messages. But how do they store messages? They store these messages in an orderly fashion. So as you can see, there is an incremental order ID, also known as offset, in each of this partition. So for partition 0, as you can see, there is offset 0, 1, 2, 3 up to n. For partition 1, we have offsets from 0 to m. And for partition n, we have offsets from 0 to x. So these partitions and offsets are useful in creating a distributed system, the Kafka cluster. Certain important points to note here is that Kafka partitions are immutable, meaning that once data is written to a Kafka partition, it cannot be altered or changed. The second important point is there is random assignment of data in Kafka clusters, which basically means that once you input in data into a particular topic, it is randomly assigned to these partitions unless you specify a message key. Also important is to note that data is kept for a limited time in these Kafka partitions, and it is by default configured to 2 weeks in Kafka. And this is natural because, everything is processed in real time in Kafka. So you cannot really process so many events and store them for a longer period of time. Also, it is important to note here that in Kafka, you have to retrieve that information within that limited frame period of time, which is, basically 2 weeks. And this actually helps, the storage space from getting exhausted. So there won't be a scarcity of storage because we are recording data in real time here. Also important to note here is that the more the partitions, the more the parallelism, and offsets have a meaning for a particular topic partition. So say, for example, I have offset 3 in partition 0, and I have offset 3 in partition 1 as well. They are not interrelated. They are totally independent of each other. Now going to another important aspect in Kafka, that is broker. So we have already discussed about brokers in our previous slide. Brokers are basically servers that are designed to serve or receive data. One important feature in Kafka is if you want to get connected to any specific broker, let's say broker 1, Kafka will connect you to the entire Kafka cluster, because you can see in Kafka, data is divided into topics and partitions. So if you don't get connected into all the Kafka cluster, then you won't be able to access the data that is split into partitions. Also, there is an important concept of replication in Kafka, which is being used for fault tolerance. Let me explain how. So as you can see in my screen, there is topic A, which has two partitions, partition 0 and 1. And there is also topic B, which has one partition, topic B, partition 1. So topic A partition 0 is replicated in broker 2. Topic A partition 1 is replicated in broker 3. Topic B partition 1 is being replicated in broker 1. So why is this being done? This is being done because if a broker crashes down or fails due to any kind of inconvenience, the other brokers can provide us with the same amount of data. But it is also important to note here that only one broker can act as a leader in the Kafka cluster at a time. Like in my example, topic A partition 0 has become the leader in broker 1. So it is only responsible for sending and receiving data from the producers and consumers respectively. The in-sync replicas, ISRs, or the replicas that it has created in broker 2, however, cannot send or receive data from producers and consumers on its own. It can just synchronize or copy paste the data from the topic A partition 0 of broker 1, since that is the leader. The other adds its replica. Two important points to note here is that replication takes place at the partition level only, and it is not possible to have number of replication factors more than the available number of brokers, because this will just cause inconveniences and a loss of space and storage. Next, going to yet another important concept in Kafka. This is called Kafka consumer group. So this is a mechanism by which Kafka consumers are grouped into one category. So as you can see on my screen, there is this consumer group, AppDB updates consumer, which has two consumers, consumer A and consumer B. And in my Kafka brokers, there is a single topic with partitions 1, 2, 3, 4. And these partitions are equitably distributed among consumer A and consumer B. Consumer A gets partition 1 and 2. Consumer B gets partition 3 and 4. And there is no duplication howsoever, and it is being equitably distributed. Also, an important thing to note here is that Kafka can actually track up to which a consumer has read the information using consumer offsets, which I'll be explaining in the further slides. And a topic replication factor, which is used for fault tolerance, is an important factor in achieving Kafka fault tolerance. And a replication factor of 2 and 3 is highly preferable in Kafka clusters. Next, going to Kafka use cases, and this is going to be interesting, of course, because I'll be providing you with real-time use cases. Messaging. So as we all know, Kafka was, created as a messaging queue. So it was basically used in messaging apps. Let's say I send a message to you and someone else also sends the message to you. You are receiving that message in real time because these events are being processed in real time and you are receiving those messages without any lag. It's like in that instant only you are receiving the messages. Also in any WhatsApp group or any kind of group, if I am sending a message and any other person is sending the message, you are receiving these messages in the order of us sending you. This is because these events are getting processed in real time and then dispatched to the target application, that is WhatsApp, as per the requirement. Next, going to the second use case, that is activity tracking. So we know that for any successful enterprise, the key is data. Data is the new oil, like we all know. So tracking the data of customers, like what they're performing on our websites, like the number of page visits or what they are searching, what they are clicking at, or what items are they adding to the cart. This can actually help us in enhancing the customer experience. Let's suppose I am a customer and I'm looking for a TV in the budget range of 40,000. And I find that the TV is basically out of stock. If a notification of this can be sent to the manufacturer in real time, he can just, say like the TV will be available within 2 days. And so I get notified about the same and I'll just return back in 2 days and check for the TV again without getting frustrated. And my experience is also enhanced, which is a huge bonus for any successful business firm. Next to it, we have gathering metrics for many different locations. So this is basically used in apps which enable us for ride sharing, like Ola and Uber. So they basically contain user data, the data about rides, the data about the drivers. So when you are using Uber or Ola, each movement of the driver, if he is moving 500 meters, 1000 meters in east, west, everything is being shown in real time on a map, right? That is for customer convenience, so that the customer isn't just waiting. He knows where the driver actually is and he can use it to his own convenience. All this is done through Kafka. Another important thing is applications logs gathering and event sourcing. So for stream processing and real-time event streaming, we basically store our data in log files instead of databases. And event sourcing is an important concept in microservices architecture. And this basically means storing the events as they occur in real time. Next, going to stream processing. This is basically processing the stream of events as they occur. And this is done through Kafka Streams API or Spark. Then, of course, decoupling system dependencies, like we saw, if we have some source systems and some target systems, they do not need to be linked directly. We can just link them to Kafka. It can act as a middleman and reroute the information or data from the producers to the consumers by acting as a middleman in a distributed fashion, which makes the system and architecture much more convenient for using. The next example or use case of Kafka cluster is definitely integration with big data technologies like Spark, Flink, Hadoop, and numerous platforms like Kubernetes or Snowflake. Like I said, I showed in the previous slide, it can be integrated with numerous tools and platforms, and that is why it's trending. Next, going to some of the big firms which have been using Kafka as of recent. So Twitter uses Storm Kafka. Storm Kafka is basically a component of Kafka. And Twitter is using Storm Kafka as a part of their stream processing infrastructure. LinkedIn is using Kafka to prevent spam, collect user interactions, and to make better connection recommendations in real time, and also for operational metrics. So let's suppose I am looking for referrals from data scientists, and I'm searching different people on LinkedIn, saying that and checking that if they're data scientists or not, because I just want to be a part of their team. So at the same time, if LinkedIn tracks their data in real time and is sending me recommendation of some data scientist profile, then I'll be happy, right? That is it. You got it. It is called enhanced customer experience, and that can be done by suggesting customers in real time and acting about the events in real time. Next, going to Mozilla. Kafka will soon be replacing a part of Mozilla's current production system to collect performance and usage data from the end user's browser for projects like telemetry, test pilot, etc. And Oracle provides native connectivity to Kafka from its enterprise OSB or Oracle Service Bus, which allows developers to leverage OSB built-in mediation capabilities to implement staged data pipelines. Next, going to Uber, like we already discussed, it will use Kafka to gather user, taxi, and trip data in real time to compute and forecast demand. So this is because, like you see, for a particular location, there are many cabs and there are many consumers as well. So depending upon demand and supply, it will basically compute the pricing, whether it has to reduce it or increase it as per the availability. And all of this is done in real time. So, it actually is a great profit to the business. And then going to Netflix. So whenever you are watching your favorite shows, Netflix uses Kafka to apply recommendations in real time. And this is not just true for Netflix, but any other OTT platforms like Disney Hotstar. And they are basically using Kafka for applying recommendations based on your user preferences. Suppose you have been watching like thriller genre the past couple of weeks. So Netflix or these OTT platforms are basically applying those recommendations in real time for an enhanced user experience. Next, going to different sectors in which Kafka is being used. The first is, of course, finance. But as we all know, banks have been a legacy system, and they are attached with a huge amount of scrutiny and security and numerous protocols. And that's why it's not really possible. It was thought that it was not really possible to implement Kafka because, in banks, processing takes 2 days. You are transferring loans or doing anything. Banks are generally slow, and they have a lot of security in place That's why it was thought that previously Kafka couldn't be implemented at the core in banks, but now many banks in USA are basically implementing Kafka as their core component. This has empowered successful core banking platform relaunch and met HA and SLA standards, and also improved scalability. And also in finance, Kafka should be used more and more because it can actually act in detecting fraud in real time. Suppose there is a transaction in my credit card and I get notified about it after 2 weeks or after 2 days. So is it really going to help me? No, right? But if I get notified about the same right now in real time, just sitting on my couch, then I can just go and block my credit card or debit card, whatever. And basically this will help to minimize risk and I won't lose money. So this will result in improved customer experience by acting in real time. Next, going to e-commerce, like I discussed, we can always have Kafka to process events in real time, events as they occur, so that we can take decisions to draw more users, give them good recommendations. This can help in improved data integration, increased upsell and cross-sell opportunities, increased sellability and flexibility, and saved cost. Also, it can give us a customer 360-degree view. So every company has a many number of customer databases, but not all of the employees actually know about all the existing databases. Kafka can actually provide an integrated platform for knowing the customer from a 360-degree view in real time and acting upon it. This will enhance performance and monitoring and project savings of millions of dollars, which is actually useful in the e-commerce industry. Let me cite an example to show this. Suppose you say you are boarding a flight, you have a flight, let's say, and it got cancelled because of some kind of circumstances. And suppose the airport authority basically understood it and got the information in real time, and then they are now onboarding you to certain different airlines, then you won't be a frustrated customer. You will be actually thankful to the airport authority that they are acting in real time and saving you time and money. And that is how acting in real time can, increase good customer reputation and profit your businesses. Next, going to automotive. So we all know that automatic cars are not really far away from the future. And by capturing events in the form of sensors, like these cars can have front and rear radar sensors, crash sensors, ultrasonic sensors, and various cameras in place, which can actually, basically capture events in real time and then process these events and can generate alerts like traffic alerts, anomaly detection, hazard alerts, or personalization, which can help us have a smooth driving experience and will be so much feasible for a driver. Next, going to two main other categories where Kafka is finding its use case. The first one is definitely banks, where you can have it in organizations which need information to be processed real fast, like raw and CBI, where if you get the information about some, let's say, some bombings or some crucial information, you can act in real time and by processing these events. So this will reduce welfare crime through strengthened identity management also. And also in various other sectors, we all know governments are kind of slow. So if we can actually implement Kafka in our government organizations, then they can actually be fast and take actions in real time. Also, another use case is in the gaming industry. So in the gaming industry, there are a lot of events taking place, like the gamer is fighting, he's getting injured, so he needs to purchase health materials or something like that. So we can basically recommend the gamer about in-game purchases, and thus we can actually expand our business in the gaming industry through Kafka. This is the truth. As you can see, all the top names in the industry, be it PayPal, Microsoft, Adidas, Netflix, Cerner, Noria, New York Times, Yelp, Bloomberg, Tumblr, Amadeus, Trivago, Dropbox, Intuit, Etsy, American Express, Capital One, Audi, everyone has already started implementing Kafka in their core architecture because they actually want customer data and they want to enhance customer experiences by utilizing this powerful platform. And this is just an exhaustive list, guys. The list is really, really big. Now that we have understood why Kafka is trending in the industry with so many number of big firms using it and implementing it in their core architecture, let's understand what are some major capabilities of Kafka. The first one definitely is horizontal scalability. So with Kafka, you can add as many number of brokers you want, and that can help you process trillions of messages per day, which is petabytes of data. Secondly, Kafka ensures high throughput, where latency is as low as 2 microseconds, which means it feels like everything is happening in real time. Next, going to high availability. Due to its clustered environment of a number of brokers, Kafka is highly available and accessible no matter where you are. Next, going to the permanent storage, Kafka systems are distributed, durable, and fault tolerant because of the replication of brokers, like I already demonstrated. And also, Kafka helps you in real-time data handling, which is because it helps you process streams at a global scale at real time, which is so impactful. Next, going to certain major challenges, because everything that has so many pros, of course, has its cons, and everything has got its own limitations. So first of all, I would like to just cover the two trivial limitations that Kafka has. The first one is once you produce a message into Kafka, it cannot be changed. Of course, that is one of the biggest limitation, I would say. And the second is the Kafka messages are available for a limited period of time, after which you have to retrieve it. But of course, this is because we cannot have infinite space. And if we are capturing humongous data, real-time data especially, we have to, make it available for a limited period of time, else we can, run out of space. The other challenges that we face while using Kafka are message tweaking issues. So Kafka broker uses system calls to deliver messages to the consumer. In case the message needs some tweaking, the performance of Kafka gets reduced. Also important is to know that brokers and consumers can reduce the performance of Kafka by compressing and decompressing the data flow. Also, Kafka does not support wildcard topic selection. The topics which are already there and will match are only applicable in Kafka. And also, Kafka lacks certain important message paradigms like point-to-point queues and request reply. And also, Kafka does not have a complete set of monitoring and managing tools. Next, going to future scope. So, Apache Kafka definitely has its limitations, like we all discussed. But which thing in this world doesn't have limitations even? And this is why Apache launched Pulsar after Apache Kafka, and this is how Apache Pulsar comes into the picture. Not only can it handle high-rate real-time use cases like Kafka, but it also supports standard messaging queue patterns such as competing consumers, failover subscriptions, and easy message fan-out. Apache Pulsar automatically keeps track of the client thread position in the topic and stores that information in its high-performance distributed ledger Apache Bookkeeper, and hence no rebalancing is needed whatsoever. So this proves us that Apache Pulsar is trying to get better at this, but Kafka still has grown its importance in the industry. Now to conclude, at present, Kafka has become the de facto standard for real-time data analytics with the highest precision in microseconds. It enjoys the prime preference for more than 70% of the Fortune 500 across the globe. Taking these milestone achievements into account, Kafka and its successors are definitely going to pioneer and shape the entire real-time event streaming narrative. And that was about Apache Kafka. We have really understood what kind of impact it has had in the current industry. With this, I would like to conclude. Thank you.
Okay, thank you, Shatabdi, for the information. And now the forum is open for questions. So if anyone have any question, they can raise their hand, or else they can put their question on the chat box. Thank you everyone for joining the session, and we will post the recording in our YouTube channel, and keep following us in our LinkedIn page, or else if you want to share any idea or showcase something, then feel free to reach out us. Thank you so much.